current electricity topic. This is section 8.3, voltage. Now, right off the bat, I want to give you some synonyms for voltage, or actually phrases, groups of two words that mean the same thing as the word voltage does. All right, so instead of the word voltage, you might see voltage drop. All right? You might see voltage drop. You might see potential drop. All right, means voltage, potential drop. You might see potential difference. Potential difference. All right, and you might see electric or electrical potential. Now, all of these, all right, these phrases here mean the same as the word voltage. Now, I will mention, as soon as you add the word energy, if this were to say electric potential energy, now they're not talking about voltage. They're talking about electrical energy or work, as in W. All right, so electric potential by itself means voltage. If it says electric potential energy, that's not voltage. All right, so be a little bit careful. These are all synonyms, all right? All these phrases are synonymous with the word voltage. Here we go, talking about voltage, and especially the difference. I want you to especially take note how the explanation of voltage in this section is different from the explanation of current in the last section. You want to have a definite picture in your mind, right, by using these little electrons, all right, to visualize what we're talking about with these little electrons. You want to have a definite picture in your mind of the difference between current and voltage, and then you'll do very, very well in the current electricity topic. All right, now as we're trying to get started here, okay, some more notes, all right? When we're talking about electricity, all right, in the electricity topic, the word work is synonymous with either the phrase electric energy, electrical energy, or electric potential energy. Electrical potential energy. All right, this is why the phrase electric potential refers to voltage, but as soon as you put the word energy on there, it refers to work. So the unit for all of this would be joules. All right, the unit for work is J for joules. The unit for electric energy, which is synonymous with work, would be joules. Electric potential energy is joules. All right, these are synonymous, these phrases and the word work. Okay, now, what a battery does work on electrons to give them a certain amount of electrical energy per coulomb. All right, so now we'll see what we mean by that. That different batteries give electrons less or more energy depending upon the voltage of the battery. Let's draw some batteries and let's see how much electric energy each type of battery gives to a coulomb of electrons. Let's look at the voltages of some common batteries and see what that means. Well, you've got your regular AA, AAA, and C and D batteries that look something like this. All right, it's a cylinder. It may be fatter or rounder, but you've got a cylinder with a little electrode up at the top. All right, and that would be, for example, a AA, a AAA, a C or a D battery. All right, they will all be 1.5 volts. All right, 1.5 volts. And what that means, all right, voltage, all right, is that this battery is going to give 1.5 joules of electrical energy to each coulomb of electrons that come out of the battery. All right, how about a 6-volt battery, the lantern battery? Lantern battery is about that high, all right, so it's a little bit bigger. All right, it's pretty much the same up on top, except it's got 2 electrodes up on the top. All right, 1, all right, 2. Okay, and this is a 6-volt. We'll call this a lantern battery, because you generally put it in a lantern when you're going camping, all right, if you want to be able to see at night. All right, so this is a 6-volt battery, and that would mean that each coulomb of electrons that comes out of the battery is getting 6 joules of electrical energy or work up on top. All right? Now you're starting to get an idea already that the unit for voltage is joules per coulomb, but we'll go into that in a little while. All right, a 9-volt battery, all right, here's a little 9-volt battery, about the same size as these guys, all right, and he's got 2 electrodes up on the top, all right, this is called simply a 9-volt battery, all right, and of course he's putting out 9 volts, all right, meaning that each 1 coulomb of electrons that comes out of the battery is getting 9 joules of electrical energy to split up amongst, remember how many electrons a coulomb is? 1 coulomb is 6.25 times 10 to the 18th electrons. All right, that's a lot of electrons in a coulomb, all right, of charge. Okay, and finally, let's do a car battery. All right, a car battery is pretty big. All right, he's got the little electrode over here and the little electrode over here. All right, one side is plus, one side is minus. A car battery is going to be 12 volts. This is a car battery. Okay, and it's going to be 12 volts. Okay, 12 volts, meaning that each coulomb of electrons that comes out of that battery is going to get 12 joules of electrical energy. All right, so you see the different types of batteries, different voltages of batteries, and it's kind of interesting that all of the small batteries that we commonly use are all 1.5 volts, but they're set up for different applications and different devices. All right, but you got 1.5 volt battery, 6 volt battery, 9 volt battery, 12 volt battery. Obviously, the 12 volt battery is giving the electrons more energy than the 1.5 volt batteries are. Okay, so voltage, joules per coulomb. How much energy in joules is each coulomb of electrons getting from the battery? All right, now the definition of voltage. All right, voltage. Now remember, there were quite a few phrases that were synonymous with the word voltage. Potential difference, potential drop, electric potential, etc. All right, so voltage, potential difference is one of the synonyms, is defined. All right, now voltage, right, the symbol is V, all right, capital V. Potential difference is defined as the amount of electric energy. Now, electric energy is work. The symbol is W, all right, per coulomb of charge. Per coulomb of charge. Charge is Q, all right. That's fine. All right, so now we can also give a preview of the equation for voltage, okay? All right, now technically, voltage would be defined as the amount of electric energy per unit of charge, but it's very, very common to use the coulomb as the unit. All right, so voltage is the amount of electric energy per, all right, unit charge, which is more often than not going to be the coulomb. All right, so voltage is the electric energy per, see the division sign? Per unit of charge, or per coulomb of charge. All right, you can also figure out what the unit for voltage is going to be. All right, work is going to be joule. All right, per charge is going to be coulomb. So joule per coulomb is going to be the unit for voltage. The word that we give to joule per coulomb is the volt. And the symbol is V. This is one of the very few physical parameters where the symbol and the unit are the same. That's very, very rare. The symbol is V, capital V. The unit is V. Also keep in mind that a lowercase v is not voltage, it's velocity. All right, so this is an uppercase or capital. Capital letter V is both the symbol for voltage and the unit for voltage. All right, and a volt is a joule per coulomb because it comes from the equation which defines voltage. Voltage is electrical energy per unit of charge. Okay? So this is an introduction to the definition of voltage and the unit for the equation for voltage and the unit that we derive from that equation. Now again, one of the problems in physics and chemistry and math is that sometimes it's very hard to visualize, to have a picture in your mind of what you're talking about. That's what makes these sciences and math, the language of science, so abstract and sometimes difficult. So we want to have a picture, all right, a model, all right, a way to visualize voltage, all right? So again, like we did in the last section when we talked about current, all right, we're going to use one dot like this to represent a coulomb of electrons. Now, how many electrons is that? Well, there's three ways that you can know how many electrons are in one coulomb. All right, first of all, on your reference tables, it says 1 coulomb is 6.25 times 10 to the 18th elementary charges. So 1 coulomb would be 6.25 times 10 to the 18th electrons, all right, according to your reference tables. So that's one way. All right, now another way. You've got 1 coulomb. You want to convert that to electrons. All right, so we want to get rid of coulombs. We want to know how many electrons. All right, so these two have to equal each other to work in the factor label method, all right, or dimensional analysis method, which is very similar. All right, we know that 1 electron has a charge of 1.6 times 10 to the negative 19th coulombs. Now, just to be exact here, we know that a coulomb of electrons would be negative and 1 electron would be negative. Those two negatives are going to cancel anyway. But we want to have a positive number of electrons. You can't have, for example, negative 6 electrons. I mean, you could say you're missing electrons, but that's not what we're trying to do here. All right, so we want to know how many electrons are in 1 coulomb. Take that 1, divide by 1.6 times 10 to the negative 19. 1 divided by 1.6 times 10 to the negative 19, right? And we get, all right, 6.25, just like we said on the front of the reference tables, times 10 to the 18th, the coulombs bottom and top cancel, electrons. All right, so that's how many electrons are in 1 coulomb. There's another way you could do this. You could think of it a different way. You're going to get the same answer. It's more or less the same math. All right? You could say that 1 coulomb, all right, of electrons is equal to 6.25 times 10 to the 18th electrons. All right? You know that. Okay, so if you wanted to figure out 5 coulombs or 6 coulombs or 20 coulombs, you could do this also. All right? The coulombs are going to cancel. 1 times 6.25 times 10 to the 18th. All right, we have 6.25 times 10 to the 18th electrons. Okay? So you can either do it this way, do it this way. Either way, you're going to get 6.25 times 10 to the 18th electrons. So this dot is going to represent 1 coulomb of electrons. It's going to represent this many electrons, which, by the way, let's just take a look at that number. All right? That number would be 6.25 times 10 to the 18th. So that's 1, 2, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right? So how many electrons is this 1 dot going to represent? How many electrons are in 1 coulomb? All right, that's thousands, that's millions, that's billion, that's trillion, that's quadrillion, all right, and that would be quintillion. So it represents, this dot is going to represent 6.25 quintillion electrons. Okay, so keep that in mind. Whenever I pull out one of these dots, it's this many electrons. It's 1 coulomb of charge, which would take this many electrons to carry the charge. So what we're going to do now is draw a series circuit to try to help you to understand what voltage means and also how voltage differs from current. Now, do you remember from the last section? Now, if you didn't watch the video right before this one, I really would like you to go back and do that video first. All right? Do you remember? You should do that. Okay. Do you remember from the last video the way to draw, right, a cell, right, these are called circuit symbols, all right? How do you draw a cell? How do you draw a battery? How do you draw a piece of wire? How do you draw a resistor? All right, see if you remember how to draw these. All right, pause the video. See if you can draw these on your own. I'll draw them in just a minute. All right, so go ahead and pause the video. All right, so now that you tried to do it on your own, see if you got it right. Okay, a cell would be a negative and a positive. That's a single cell. If you put two or more cells together, you have a battery. So negative, positive, that would be a battery. A wire is just a line. It can be horizontal or vertical. And a resistor, right, would be, all right, a zigzag, like that. And usually a resistor is connected to wire, so we'll put a little bit of wire at the beginning and a little bit of wire at the end. It doesn't matter how many zigzags you make. Don't get crazy. Three zigzags is great. 4 zigzags is fine. More than that is too much. Right, less than that, probably not enough. 3 or 4 zigzags is usually pretty good. Right, so these are the circuit symbols so that you can draw a circuit. Right, now, we're going to draw a series circuit with one battery. We're going to make it a 10-volt battery. All right, that wasn't one of the common batteries that we talked about before, but there definitely are 10-volt batteries out there that people use. All right, so we're going to draw a circuit, a series circuit, all right, a series circuit, and we'll talk in a different section about the difference between a series and a parallel circuit. All right, a series circuit with, right, one 10-volt battery, all right, and 2 resistors. Okay, so here's the battery, right, negative, positive, negative, positive. All right, we take a piece of wire, we go up, we make a resistor, okay. Let's get a little too much there. We make another resistor. So we have 2 resistors, okay, and we have a 10-volt battery. All right, so I'm going to label that this battery is 10 volts, okay. Now, if you remember from the last section, all right, the number of coulombs that pass by per second is going to be your current. So we're going to make the current here, we're going to make the current 6 amps. All right, so 6 coulombs, 1, 2, 3, 4, 5, 6 coulombs are coming out per second. All right, and furthermore, talking about voltage now, each of those coulombs has 10 volts of energy. So this guy has 10 volts, 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 10 volts, 10 volts, etc. Now, it could be, since this is energy, right, this is how much energy each coulomb has. All right, now, let me just remind you again, we've got 6 amps is the current, all right? The current is 6 amps, or 6 coulombs per second. The voltage is 10 volts, or 10 joules per coulomb. All right, keep that in mind. Current and voltage are not the same. All right, so this guy has 10 volts. Now, it's 10 joules for this 1 coulomb. Now, he can give 5 volts to this resistor and 5 volts to this resistor. He can give 6 volts to this resistor and 4 volts to this resistor. All right, this resistor could get 2.5 volts, and that resistor could get 7.5 volts. As long as whatever he gives to him plus whatever he gives to him, he goes back empty to get more volts, all right? And the 2 of them have to obviously add up to 10, all right? And whatever this guy gives the same. So let's just say, for example, right, that this guy is getting 6 volts and this guy is getting 4 volts, okay? So here comes, remember that the current is 6 amps, 1, 2, 3, 4, 5, 6 coulombs per second, all right, and the voltage is 10 volts. This guy has 10 volts, this guy has 10 volts, this guy has 10 volts, etc. So this guy gives 6 volts here and 4 volts there and goes back empty for more energy. 6 volts here, 4 volts there, goes back empty to get more energy from the battery. This guy gives 6 volts here, 4 volts here, goes back to get more energy, etc. 6 plus 4 is 10 volts. 6 plus 4 is 10 volts. 6 plus 4 is 10 volts. Okay, this is what voltage is. This is how voltage is different from current. And this is how voltage works in a series circuit. All right, for current, you're counting the number of coulombs per second. All right, this is 6 coulombs. 1, 2, 3, 4, 5, 6 coulombs every second. Every one of these coulombs has 10 volts of energy. All right, and the voltage of this resistor plus the voltage of this resistor adds up to the total voltage for the series circuit. Okay, so 6 plus 4, now he's empty, goes back for more, right? 6 plus 4, goes back for more. 6 plus 4, goes back for more. Oh, I'm loving this little rhyme here. 6 plus 4, he goes back for more. 6 plus 4, he's empty, he goes back for more, etc. 6 plus 4, he goes back for more. Okay? So current and voltage are not the same, and voltage is the energy for each coulomb, the energy per coulomb of electrons, and if you add up the voltages of all the resistors in series, that gives you the total voltage out of the battery. A battery can also be called a power source. Now we're going to draw a parallel circuit, one 10-volt battery and 2 resistors, and we're going to see how the voltage is a little bit different for a parallel circuit than it was for a series circuit. All right, so we draw a 10-volt battery, all right, negative, positive, negative, positive. There's the battery. This is going to be a 10-volt battery. Here's the wire. All right, remember how we did the parallel circuit in the previous section? Here's the resistor, okay? And here's another resistor. I'll put it over here. Okay, so now we have 2 resistors in parallel. So here we are, about to analyze a parallel circuit with one 10-volt battery and 2 resistors. Now, I'm going to use a current of 6 amps. 6 amps would be 6 coulombs, 1, 2, 3, 4, 5, 6, per second. We learned that in the previous video. Now, I want you to remember that each dot is going to represent 1 coulomb of electrons. That means each dot is 6.25 times 10 to the 18th electrons. All right, so this represents 1 coulomb, 2 coulombs, 3, 4, 5, 6 coulombs. And if the current is going to be 6 amps, then these 6 coulombs must go past this point, for example, in 1 second. Now, I also want you to remember about current that at this juncture here, the current in a parallel circuit is going to divide. Some of it is going to go through this resistor. All right, I'll have 4 amps go through this resistor, and 2 amps go through this resistor. So the currents in a parallel circuit, as you recall, are not the same. The total current coming out of the battery was 6 amps. 2 of the amps went this way, 4 of the amps went that way. It could have been 3 and 3. It depends on the resistors. We'll go into this in much more detail in later videos. Now, when these coulombs get back to here, you see that the total current is back to 6 amps. So here we have the 6 amps going back into the battery. Looking again very quickly at the equation for current, all right, current equals charge per unit time. All right, that would mean that if we had 6 coulombs passing by every 1 second, All right, the current would be 6 amps. All right, so again, current is charge per time. All right, how many coulombs are going by in a certain amount of time? Now let's look at voltage and how voltage is different from current. The voltage that this battery supplies is 10 volts. The equation for voltage, V equals W divided by Q, that would be the amount of work done on each coulomb. All right, so this would be the joules, in this case 10 joules per each 1 coulomb of electrons. All right, so that means that this coulomb gets 10 joules, so its voltage is 10 volts. This coulomb gets 10 joules, so its voltage is 10 volts. The joules, the energy, is coming out of the battery, so the battery supplies 10 joules to this coulomb. That's 10 volts. So each of these coulombs has 10 volts when it comes out of the battery. All right, now, let's say, for example, that this coulomb of electrons heads down this branch of the parallel circuit. That means that this coulomb dumps all 10 of its volts onto this resistor. All right, this resistor uses all 10 volts. And back goes the empty coulomb to get more energy from the battery. All right, now here comes another coulomb of electrons. All right, so this 10 volts comes through here, all right, and deposits its 10 volts right there. All right, we'll continue to use 3 significant figures. All right, so this coulomb of electrons gives its 10 joules of energy to this resistor, and the empty coulomb goes back to get more energy. So you see that the voltage across each resistor is going to have to be the same as the voltage across the battery. So in a parallel circuit, zip, all right, in a parallel circuit, 10 volts, zip, this guy, 10 volts, zip, this guy, 10 volts, zip. In a parallel circuit, all of the voltages are going to be the same. The total voltage is 10, the voltage of this resistor is 10, and the voltage of this resistor is also 10. Okay, so just a quick summary how voltage and current are different in series and parallel circuits. In the series circuit here, we have a 10 volt battery. In the parallel circuit here, we have a 10 volt battery. All right, that means that the total voltage here is 10 volts. And I'm just going to make this 2 significant figures so we can make it a little shorter. All right, now, let's just say that the current is 6 amps. All right, so the current is 6 amps. Now, that means that, for example, this coulomb here has 10 volts coming out of the battery. All right, so it could be that this resistor gets 5 volts and this resistor gets 5 volts. That's if the 2 resistors are the same. This resistor would get 5 volts and this resistor would get 5 volts. But since all 6 coulombs must go through each resistor, the current in each resistor is 6 amps. All right, so again, if this coulomb has 10 volts, it has to give some of that energy to this resistor and some of that energy to this resistor. It could be 5 plus 5. And then it's empty and it goes back to get 10 more volts. But again, all 6, 1, 2, 3, 4, 5, 6 coulombs must go through each resistor. So the current in each resistor is the same. So take a look at this. All the currents are equal in a series circuit. 6 amps for the total current, that's the battery. 6 amps for this resistor, 6 amps for that resistor. But for the voltages, you add them up. 5 volts plus 5 volts equals 10 volts. All of the voltages are not the same. But if you add up all the individual voltages, 5 plus 5, it's going to equal the total voltage. So in a series circuit, the currents are all the same, 666. The voltages, you add up the voltages to get the total voltage. 5 plus 5 equals 10. Currents are all the same, equal. Voltages, add them up to get the total. Moving on to a parallel circuit. In a parallel circuit, okay, this parallel circuit has a 10-volt battery, just like the series circuit we were just looking at. We've got a 10-volt battery. Now, we're going to say that the current coming out of the battery is also 6 amps. All right, so we've got 1, 2, 3, 4, 5, 6 coulombs every second. So the current is 6 amps. All right, now, the voltage, all right, this coulomb gets 10 volts. And if this coulomb heads down this branch, all 10 of those volts go to this resistor. And then this coulomb goes back to get more joules so that it will have 10 volts again. This one has 10 volts. Let's say he goes down here. All right, so we've got 10 volts here, and then it goes back. All right, so 10 volts, all right, 10 volts, all right, 10 volts, 10 volts. Now you know the battery is 10 volts. It's supplying 10 volts to each coulomb of electrons. All right, now, if 3 of them went this way, all right, 1, 2, 3, and 3 of them went this way, 1, 2, 3, all right, then you know that the current here was 3 amps, and the current here was 3 amps. So see how the parallel circuit is different from the series circuit. In the parallel circuit, all of the voltages are equal. 10 volts, 10 volts, 10 volts. For the current, you add them up. 3 amps plus 3 amps gives you the total 6 amps. Now there are other combinations that are possible. I mean, obviously this could be 2 amps and 4 amps, right? Or this here could be 6 volts plus 4 volts. Right, so there are other possibilities. The possibility I'm looking at here is when the 2 resistors are the same. When these 2 resistors are the same. Right, but what you want to get out of this, in a series circuit, the currents are equal. For the voltages, add them up. In a parallel circuit, the voltages are equal. For the currents, add them up. That's what you want to get out of this.